And when we get down to here, right, the Q values are irrelevant at this point. We're just thinking of these abstract states and how we move from one to another. And the only thing that really matters is the inputs and the outputs and the states themselves. Let me tell you the full story about outputs. And this is confusing on a good day. Okay, it actually took me about 3 times teaching this course before it finally clicked for me. So I want to mention it just so that when you see it in the book, you know at least what it's talking about. But don't get too concerned if this is confusing. Okay, so I made up some outputs here, and then I had to change my mind, right, and scribble these out. Why did I do that? Because in this case, where x was 0. State D, the outputs were 1, 1. But in this case, where x was 1, state D, the outputs originally I had 0, 0. The outputs depended not just on the state, but also on the input variable. Okay, some machines that we build, that will happen. Some machines, it won't. There's 2 fundamentally different classes of state machines. So the machine that we worked with here after I made these corrections, this is called a Moore machine. And in the Moore machine, the outputs depend only on the state. And when we draw a state diagram for this, we can do it like this. Right? We list each state, we put a line under it, we list the outputs for that state, and then our transition arrows, we list the inputs. And we can do this because if we know we're in a given state, we know what the outputs are. It's unambiguous. But there's a whole separate class of machines called Mealy Machines, which I may have spelled wrong. And the outputs there depend on the state and the inputs. And so for a Mealy machine, we list our outputs differently. We would list our states inside circles, but on our transition arrows, we would list the inputs, and then a slash and the outputs. The reason being, we can't just put it in here because it also depends on the input value. So this would be the output if you were in this state and this was your given input or set of inputs. These would be the outputs. But I'm only been talking about Moore machines, and I'll pretty much stick with just talking about Moore machines, but there's some Mealy machines in your homework. But you can turn a Moore machine into a Mealy machine, you can turn a Mealy machine into a Moore machine, okay? They're mathematically equivalent to each other. So you don't gain anything theoretically by having one versus the other. So I'm sticking with Moore machines for this, and I'll stick with Moore machines on your tests. Okay, so your state will depend, your outputs will depend on your state. And you can represent the outputs in each state bubble. All right, you want to run quickly through this up here and then go into groups and work on number 10? Because this one has an input and an output. So let's go ahead and see what that looks like. All right, I don't like calling on people, so I'm going to call on rows and maybe sides of the room. And if you don't know the answer, you can say pass. Or if nobody answers, we'll go on to another row. So let's work with this machine. Okay, so back row, how many flip-flops? 2. All right, middle row, how many states? 4. All right. How many states do we have? 4 states. Let's name them and make a state assignment table. So, somebody give me a state name for the first state. A. Someone give me another name.
E.
Oh boy. Next one. E. And Y. Thank you. All right, we got 4 states. We're definitely going to ignore Y1, Y2 in here now because we've got Y as a state. All right, and we have 2 flip-flops, and they're labeled Q2 and Q1, so I'm going to put them in this order, which is my preferred order. And I actually prefer calling them Q1, Q0, but since it's Q2, Q1, we'll stick with that. Okay, but if I was making this up, I would start from 0. All right, so what value should we use for state A? What pair of values for Q2, Q1? 0, 0. Okay, how about for B?
0, 1.
How about for E?
1, 0.
Okay, be that way. And Y will be a 1, 1. That's good, because that's the way that I would prefer to do it. So, but again, it's not precious. It could be anything. All right, so we've made a state assignment table, each state in terms of the Q output combinations. Step 3, write outputs for the flip-flop inputs in terms of Q and the external inputs. So these are, again, D flip-flops, making my life easy. 2 inputs, D1 and D2. So let's write equations for them. So D1, so where does D1 come from? What kind of gate? It's an AND gate. Okay, what are the 2 inputs to the AND gate? So X, and the other one comes over here, across, comes down. That's an input, comes down here, and it's being driven from right here. So I'm going to call it Q2. It's also Y2, but that's basically Q2. So D1 equals X ANDed with Q2. And then D2, bless you. D2 is right here. Where does that come from? Right, so that's an OR gate. Q1. And so one input comes from here, Q1. The other input here comes from Q2. Right, because this is going to another input, so it's not driving it. So the inputs to this OR gate are Q1 and Q2. So D2 is just Q1 ORed with Q2. Everybody okay with that? Yeah. All right, and then we also have an output, so we need to write an equation for the output Z. And what would that equation be? Yes, exactly. So here, I turned this into an OR gate. So that's an OR gate that we just looked at. It's Q1 or Q2, and it goes into an inverter. So Z is actually a NOR. Q1 or Q2 bar.
Does D2 not do anything there?
D2? D2 comes from this OR gate, right? So we wrote that down, and it's going to eventually change the value of Q2.
Okay.
Yeah. Right, and as we hope, both of these flip-flops, the clocks are being driven in parallel. So that system clock is just driving those. So one input, one output, 2 flip-flop values, 4 states. We're done with the picture. So now we can just stick to what we're writing. So we've got the equations for the outputs of the flip-flops, for the inputs of the flip-flops, and we've got the equations for the outputs of the system. And X affects D1, but it doesn't affect D2 or Z, that's fine. Okay, make our state transition table. So big wide sheet of paper, nice fine point pencil, big eraser, okay? The neater you do this, the more carefully you do this, the easier it will be. And you'll make mistakes when you're doing this, okay? I make mistakes when I do this. I've been doing this for more years than I want to admit. If you can work neatly, right, and make sure that you understand what you're doing and go back and look at it, it's going to make it a whole lot easier to get through the table, to analyze it, to make your diagram, and to go back if something went wrong and figure out where the misstep was. Okay, so we want 1 row per input and state combination. Well, we have 4 states and we have 1 input, so how many rows? 8 rows, right? So present state, I should probably start on a bigger sheet of paper. So present state, and 1 input X, and I'm deliberately doing this in a slightly different order from last time because it doesn't matter. Your goal is just to make sure you've listed all the combinations of state and input variables. So 4 states, 1 input, and I just break them into 4s to keep things lined up better. Okay, so those are going to be the 8 rows of our transition table. List the current Q output values for the given state. So use your state assignment table and list the values for the current Q2 and Q1, and you're just copying from here into here. So for an A, both of these are 0. For a B, they're equal to 0, 1. For an E, they're equal to 1, 0. And for a Y, they're equal to 1, 1. So we've just copied those over from our assignment table. And then list the corresponding output values. So we have a single output Z. And remember, Z is equal to the NOR of Q1 with Q2, right? We found that already. So OR these and complement, right? If they're both 0, the OR is going to be a 0, so the output will be a 1. And if either or both input is a 1, the OR will be a 1, so the complement will be a 0. So this is just a NOR truth table. So either work through it like that or look it up in your notes. So that's what the output values are. And then list the flip-flop inputs. So now we have to fill in the values for D1 and D2. So D1 is X ANDed with Q2. D2 is Q1 or Q2. Right, we had those. All right, so somebody tell me the value for D1 in this first row. Second row. Third row.
0.
Fourth row.
0.
Is there any row where it's not going to be 0?
The last E1 and Y1.
This is a 1 and this is a 1. That's going to be a 1.
Oh, whoops, that was a
And also E1, you're right. So when you start doing these, right, you can work through it very sort of methodically, very mechanically, but you're going to start to discover shortcuts, right? And that's good. You're going to start to realize things like, hey, I don't have to fill in all 64 of these rows. I just have to look for the ones that are 1 or the ones that are 0, right? Because there may only be a particular combination that's going to give you a certain value. And you might just go through, find those, fill them in, and then fill in the rest with the other value. Okay, so you'll discover those along the way. Whichever ones click for you, those are the shortcuts that are going to be useful. All right, D2 is Q1 ORed with Q2. Anyone know a shortcut for doing that? Yeah, it's just the complement of Z, because this was Q1 or Q2 bar. So I'm just going to flip the Z column. I'm going to have faith that we did Z correctly. There's D2. All right, I'm going to make it to lunch at this rate. All right, so we've got the flip-flop inputs. And then the famous step 5, right, list the next values of Q based on the flip-flop inputs and the behavior of the flip-flops. So now we make a column for Q2 plus, Q1 plus. And I did something I would recommend avoiding. I switched the order of things. I got Q2, Q1, then I had D1, D2. That's just inviting confusion, right? But let's invite it. All right, so we want the new value of Q2 after the clock tick. What is that based on? Just D2. And D flip-flops, we can just copy over, right? Now, don't just blindly copy. Think about a D flip-flop. Go back to the transition table for a D flip-flop. Think about what's happening when the clock ticks. But then eventually it's like, oh, wait, this is just going to be whatever D2 is, so I can just do this. Same thing with Q1, it's going to take on whatever the value of D1 is. All right, now we're done with the new values of Q. The last step, list the next state based on those outputs. So one more time, back to your state transition table, your state assignment table. Q2, Q1 is 0, we're in state A. Q2, Q1 is 1, 0, that's state E. And here I'm going through and finding all my 1, 0s, calling them E. And then 1, 1, that's state Y. So this is our next stage. And now we're good to go ahead and make our transition diagram. So I didn't leave a lot of space. Let me see if we can squeeze it in down here. And if we look at our equations for our output, it only depends on the current state, Q1 and Q2. So this is what type of machine? It's a Moore machine, good. Right? If there was an X in here, this would be a Mealy machine. Okay, since it only depends on the current state, we can go ahead and we can list the output in each state circle. So if we're in state A, the output's 1. Every other state, the output is a 0. And then we just draw transition arrows. So if you're in state A and your input is a 0, we stay in state A. If you're in state A and your input is 1, we also stay in state A. If you're in state B, it looks like you go to state E. I mislabeled my states. A, B, E, Y. If you're in state B, it looks like we always go to state E regardless of what our input is. So we go there for a 0 and we go there for a 1. If you're in state E, yes?
What's the values that are under our letters?
That's the output, so let me put the key here. So here's the state. Here's the value of z, and we're listing the value of x on our input, on our transition arrows.
Okay.
And this is important. If you have three inputs, x3, x2, x1, right, you would list on your key x3, x2, x1, and then when you see 1, 1, 0, you know x3 is 1, x2 is 1, x1 is 0. So it's showing you the order of these things. With just one input and one output, it's pretty unambiguous. All right, so if you're in state E and your input is 0, you're going to stay in state E. What if you're in state E and your input is 1? Go to Y. If you're in state Y and your input is 0, you go to E. And if you're in state Y and your input's 1, stay in state Y. There's your whole transition diagram. So just thinking about this diagram for a minute, anything peculiar about it? If you're in A, you stay there forever. There's no way out. It's probably an illegal state, right? And you would probably want something in your circuit to make sure you never end up in state A. Because if you want to be in state A and stay there forever, you don't need a state machine. You don't need anything. You need a battery or something. And then this other piece of it is kind of interesting. If you happen to be in state B, you leave and you never go back to state B, right? There's no way into B. So that's probably an illegal state, maybe, or maybe it's, you know, just a one-time initialization. And then you kind of bounce back and forth between E and Y depending on your input. If your input's 1, you go to Y and you stay there. If your input's 0, you go to E and you stay there. So then your input lets you change from one of those states to the other and back. So I have no idea what this machine might actually do, but we could dream up some sort of use for it. But our goal is just to reduce it to this transition diagram. Yes?
If you can see from it goes from B to E, 0 and a 1, you have to make two separate lines for that?
I would make two separate lines unless you're really, yeah, make two separate lines.
Because what I did is just the 1/0.
Yeah, which is fine because I'll know what you mean, but if we have a Mealy machine, we're going to usually use a slash to list the outputs also.
Gotcha.
So you could do something like a comma and such, but for academic purposes, I would just do multiple arrows.
Sure.
Yeah.
Do you remember how to define the difference between more and Mealy?
Yeah, put it on your notes because it could be like a conceptual short answer question. So more outputs are determined only by the state. Mealy, they also depend on the inputs.
I was gonna say, I just found a mnemonic that said more depends on less.
Oh, nice. I like that. Okay, so more depends on less. That's cool. How did you find that?
Just online.
Oh, I didn't know you were online.
No, not right now.
Oh, okay, you did it before. Okay. Thought you had like implants or something. You really cool. Awesome. I like that. More depends on less. Okay. The other difference between a Mealy and a Moore machine, they kind of have a fundamentally different feel because we're talking about synchronization. Everything happens on the clock. But when you have a Mealy machine, suddenly your outputs can change in between clock ticks, right? And that's not always something you want. A Mealy machine, the clock ticks, you go into a state, your output's set up to whatever value they have, and now one of these inputs changes and suddenly your outputs change, right? So it feels a little less synchronous in some settings. A Moore machine, you can change that input 100 times, the outputs are not going to change until the clock tick. And then they're going to change along with everything else in the system. So it feels a little more synchronous. So that's why I tend to focus on Moore machines. All right, let's break up into, I think we can fit 5 groups pretty easily. So find some friends and grab a spot on a whiteboard, grab a marker, grab an eraser. There's several erasers around here. And grab a cheat sheet. So here's one cheat sheet. I'm going to turn on some lights, so watch your eyes.
I'm just going to take this because it's
I'm going back.
It's kind of hard.